Hello, I'm Martin Issos. I'm from the Institute of Thermomechanics of the Czech Academy of Sciences, and for the purpose of the 21st OpenFOAM Workshop held in Guimarães in the beginning of summer 2026, we prepared a short tutorial on using our particle resolved CFD-DEM solver called OpenHFDIB-DEM. So let's go to the tutorial itself. So as I said, we'll be talking about particle resolved method for computational fluid dynamics coupled with discrete element method that is fully implemented in the OpenFOAM library. So over this course, which comprises either several videos or, if you are in person in Guimarães, one single session, we will try to recreate our logo animation, which comprises an impeller and some glitters that flow around it. Outline of this course is: first, I will provide some general information about our OpenHFDIB-DEM solver. Then we will have a hands-on session or a tutorial for adding solid bodies into the domain, for possible movement modes of the solid bodies, for setting up our discrete element method, and finally for running the fully coupled CFD-DEM. In this particular video, I will provide a general overview of our method or of our solver. So with this, I will have some introduction, what interests us and so on. Then I will go very briefly through the fundamentals of our solver, through its architecture and through general workflow. So first, let's show what the solver can do. And here we have three different cases. The first one, the rock column, it's a single phase. It's a set of solid bodies that tumble down and repose. These are non-spherical solids. You can see a representative particle in here. The second case, it's a two-phase flow where we have single-phase fluid and fluidized bed of highly non-spherical particles that you can see in here. And the last case, and to be frank, this last, with respect to coding, is still under construction, but the last case is three-phase flow where you have two fluid phases and one more solid phase that is moving. And it's as you can see in here, it's immerse boundary method with volume of fluid and discrete element methods. So these are just some showcases that can be solved using our OpenHFDIB-DEM library. About the sources of information in this video, here I will try to be very brief, but if you are interested in more detail, you can go to any of these QR codes. We have some initial publication where the method is detailed quite a lot, but now it's slightly outdated since it was published in 2022. And the library was summarized in 2024 in a short software X publication. We have some algorithm and some potential application for physics studies in this 2024 publication. This QR code, similarly to QR codes shown in between the sections, will take you to the code repository, and this one to our Doxygen documentation. So in the following very brief introduction to the solver or to our library, then these are information sources if you are interested in a bit more detail. So now let's go through solver or library fundamentals. So the goal in here is to have, I will try, this should have been video, but it doesn't matter. So we have our flow, in this case two-phase flow with moving solids and single fluid phase, and in here are outlined the main interactions that we are trying to solve. So first we have particle-fluid interaction. This we do through immerse boundary method. So it's fully resolved and fully closed formulation. We do not need any drag or lift coefficients from correlations. We solve the drag or the particle-fluid interaction using the immerse boundary. For particle-particle interactions, we use soft discrete element method. When we try to place our approach on the vast landscape of modeling approaches for these particle-laden flows, so we have whole CFD modeling of fluid-solid multiphase flows, and the first branching is Eulerian approaches or two fluids models or something similar to that, and Eulerian-Lagrangian approach where we take fluid as Eulerian medium and all the particles as Lagrangian medium. So we have scale here on the bottom axis and accuracy. Of course, the more accurate solver you use, the smaller system is available to you. And in this, we are here. We are in CFD coupled with discrete element method, and our collisions are solved through the soft discrete element method. When we take a look at possible approaches to CFD-DEM for non-spherical solids, which is even, it's a subpart of this whole CFD-DEM, we can create non-spherical DEM particles using clusters or clumps of spheres. We can use some more complicated analytical expressions like superquadrics, or we can use STL files to have polyhedron-based solids. With respect to CFD-DEM coupling, we can have unresolved approach where we have several or lots of particles in a single computational cell, and these require closure models. Or we can have, on the other side, we can have fully resolved approach where single particle spans quite a lot of computational cells and the fluid-solid coupling is resolved directly through some variant of immerse boundary method. Our approach is, as before, on the most expensive side basically. So we have polyhedron-based solids primarily, and we have fully resolved or particle resolved CFD-DEM coupling through immerse boundary method. When we take a look in a bit more detail into that, so we have our fluid, which is Eulerian medium, and we have our solid particles or the Lagrangian elements. The fluid, for the fluid we solve using standard Navier-Stokes equations, in this case in incompressible formulation, and for particles, for each particle we solve Newton equations of motions for translation and for rotation. These two are coupled through this FIB, so through this forcing term, which stems from immerse boundary and is responsible for drags and drag-caused torques acting on particles. Even bit more detail on this immerse boundary approach that we use. We have stationary finite volume mesh, and we project the solid phase using some color function. We call it lambda field, which is 1 inside the solid, 0 outside of it, and somewhere between 0 and 1 on the solid fluid boundary. And this forcing term, this FIB, is active only when this in parts of the domain where this color function is non-zero. Then we can formulate the term in such a way that we fulfill boundary conditions on the fluid-solid interface. When we solve for this. With respect to discrete element method, or with respect to contact between different particles, we solve it through this soft DEM. So we do not solve for body deformations, but we allow for small overlaps between particles. This is extremely augmented view, and we scale the solid-solid interaction based on the overlap volume between particles in contact. So this is our overlap volume, and it plays a role together with a reduced Young modulus and damping coefficient, which itself is based on coefficient of restitution. So material properties and overlap volume are responsible for the scale of our contact force. For the directions of the contact force, we identify contact plane and play with that. For more detail, go see the detailed publication. I think it's outside of the scope of this presentation. So let's go for solver architecture. How is all of this actually implemented in OpenFOAM? So altogether, this is monolithic. We have both the solvers for fluid in OpenFOAM, and also we implemented our own discrete element method in OpenFOAM. So everything lives in a single code, and everything is launched through a single binary. And as a result, everything has access to all the different parts of runtime memory. With respect to a specific architecture, we have our OpenHFDIB-DEM, which is the main part of the code. And this is the main library, and it's connected to the solver. In theory, it can be connected to any solver available in OpenFOAM. In practice, we have it connected with a Pimple foam, and we are working on connections with interfoam and interisoform. And apart from that, we have one specific solver that takes care only of DM, in which no fluid plays any role, but it's placed on the standard OpenFOAM solver architecture landscape. So this is our main library interface. It takes care of all the solid bodies in the domain, and each solid body is represented by its own immersed body object. And this immersed body object is initiated by something that we call add-model. So it's a type of approaches to solid body addition to the domain, and with geomodel, which takes care of the solid body geometry. In geomodels, we can work with spheres, with convex, non-spherical bodies defined through STLs, and with complex shape, non-convex, non-spherical bodies defined through STLs as well. When you take a look at the code itself, it follows the standard OpenFOAM approach. So in the main library, we have applications with showcase solvers for incompressible, for pure DEM, and under construction also for multi-phase flow. We have this standard source code directory, in which we have the discrete element method, our immersed boundary implementation, the contact models, geometry handling, and all the technical stuff. We have some tutorials which are easy to evaluate and ready to run cases. We have examples with slightly bigger cases and some verification and validation tests, and showcases for different particle geometries, and of course we have some documentation. And if we take a look at this source code directory, there is only this HFDIB-DEM folder, and we have these add models, contact models, and all the standard stuff in there. So finally, for general workflow with our library, we follow the standard OpenFOAM practices with only minimal changes required on the user side, or this is our goal, to require only minimal changes with respect to usual OpenFOAM usage. So in each case, in initial conditions, there are all the standard fields that you are used to from OpenFOAM, But additionally, we need initial condition for lambda field, which is the which is the color function that we use to define the position of solids in our computational domain, and we need initial condition for F field, which is a forcing term, this Fi forcing term due to the immersed boundary. In theory, we wouldn't need them, but we keep them as mandatory input fields just for the user to be fully aware that these two fields are absolutely important for our solver. Then the main difference between standard OpenFOAM and usage of our library comes in this HFDIB-DEM dict located in the constant directory that actually contains all the DEM and CFD-DEM settings in a single place. So if just outlining its standard content in a slightly more detail, in there we specify, for example, interpolation schemes required for immersed boundary. We define the solid bodies that should be in the simulation, so we define their names, their types. Is it sphere? Is it convex body? Is it non-convex body? We define how this particular solid can move. Is it static in the domain? Does it have prescribed translation or rotation, or is it fully coupled with the fluid? And we define how this solid body should be added to the domain. Is it added only once on a specific place in the domain, or is it added repeatedly on the same place or at different places in the domain? Then we need to describe DEM settings, so the time step for our discrete element method, the solid materials, collision patches, and how the contact should be treated. And then, of course, some output controls for the library itself. How much of output does the user want? And with this, I would end this video and invite you to follow the next one, which will be focused on adding solid bodies into the computational domain. So thank you for your attention and see you later.